It is 8:58 a.m., the 27th of May, 2025. This is the history of mathematics. This is lecture 3. Lecture 3, Greek mathematical mastery. So last time we covered the foundational elements of Greece on math. Now we're going to proceed. That's delicious. On further mastery, starting with Archimedes of Syracuse. Around 287 to 212 BC. That's chapter 6 in Boyer and Mirbach. So we're basically going to be focusing on Hellenistic Syracuse and Alexandria, which, as some of you might know, was the focal point of the Punic Wars. Well, at least the first two. It sort of dwindled down into the second, and then the third it's kind of irrelevant. But this is an interesting individual, certainly because of well, let me check the camera real quick. Right, Archimedes is sort of the Da Vinci of his time. If you manage to get rid of the artwork, well, if you take away the art, at least in the literal sense, and focus instead on the multifaceted nature of this individual. He was a mathematician, a physicist, an engineer, an inventor, an astronomer. Archimedes didn't just extend geometry, he rapidly advanced it to new heights. In the middle of a war, he calculated volumes no one had imagined. In a bathtub, he reshaped hydrostatics. He worked the edge of finitude, trying to square the infinite with rigor. This is mathematics' physical intuition made proof. And the area that he inhabits, Syracuse, is on an island just off the coast of Italy, and is, well, the Italian peninsula. Let's go ahead and draw the tip of the boot there. That whole thing. Syracuse, right over here. Yeah, right over here. And this is being fought between Rome and Carthage, what I believe is the Second Punic War. Carthage, of course, being here in Africa. So Archimedes is going to be here in Syracuse on Sicily. So let's look at the first problem. Let's look at one problem that Archimedes was interested in and how exactly he went about solving it. So, can a dead weight balance thought? Why do some weights balance and others tip the scale? Aristotle speculated, Archimedes proved. The Archimedean breakthrough, using a postulate of symmetry, he deduced the law of the lever. Weights balance when they are inversely proportional to their distances from the fulcrum. So, can a dead weight balance? or not, or not, or not. Okay, the law of the lever. So let's go ahead and draw this. What I mean whenever I say these things. Now this is a balanced lever. I mean, my drawing isn't exactly the best, but a balanced lever with equal weights, placed symmetrically. Archimedes uses geometric symmetry to derive the conditions for equilibrium. Mathematics can explain physical reality not by simulating it, but by abstracting it. So this idea that in thought it really should be able to balance, it really should be able to have an equilibrium. And then experimenting from that hypothesis and confirming it with physical rigor, empirical rigor. And this is fairly in line with Greek thinking. Most of it's not really a matter of motion, but balance. Not forces, but geometry. Let's go ahead and write out the law of the lever. Weights balance when they are inversely proportional to their distances from the fulcrum. So I'm just going to check the camera while I let that kind of settle in. Camera's looking fine. And this is the fulcrum, of course. Just right here's the fulcrum. Now, we mentioned earlier the eureka moment that Archimedes supposedly had in a bathtub. Story goes, as such, Archimedes leaps from a bath shouting eureka. And the real insight here that he finds is a body submerged in a fluid displaces an amount of fluid equal to its own weight if it floats. The scientific contribution of this moment is that Archimedes did not merely observe buoyancy, he derived it from principles of pressure and equilibrium. This is perhaps the first formulation of a physical law derived from mathematical reasoning. Nature floats on number. Physical phenomena obeys laws not just observable, but provable. So, let's say this is a bathtub here. Archimedes is in a bathtub like so. Water rises accordingly. Like take a ball, you put it in a pipe or a cylinder, put it in there, it will rise to another level because of the displacement going on. Simple. But not too easily to formulate if you're just sort of starting out. And well, hindsight is 20/20. Something I find more impressive. He asks himself the question, how do you count the sand in the universe? Now, this is largely a metaphorical thing because, well, how would you really confirm that empirically? Counting each of them bit by bit. It's like, nope, can't do that. It would take you way too long. So, there's this thing by the name of the sand reckoner. And Archimedes comes up with his own sort of number system. really it's early exponentiation. The Greeks lacked a system for naming extremely large numbers. Their mathematics topped out at around a myriad. The Greek upper limit is a myriad, which is equivalent to 10,000. So the highest you can go is 10,000 when using the previously established Greek upper limit. But Archimedes devised a system by which he could look at myriads of myriads. Sort of a recursive notation system. That could look at numbers like 10 to the 8 times 10 to the 8, 10 to the 8 times 10 to the 8, not, yeah. If you were just listening to it on voice, you wouldn't be able to distinguish, I suppose. So what's the real context of this? Why would he be asking, how do you count the number of sand, the number of grains of sand in the known universe? Well, he used this to calculate how many grains of sand would fill a universe large enough to accommodate the heliocentric model of Aristarchus, a world that dwarfed Earth insofar as the Greeks could conceive. To do this, Archimedes grouped numbers into orders, each representing a new layer of magnitude. One order could express up to a myriad of myriads. Then he built periods from orders, a structure of exponential stacking. This was not just big arithmetic, it was the architecture of scale. The infinite begins not in space here, but in notation. Naming large things is the first step in measuring them. Think of it like a scientific notation nested in scientific notation. And I'll show you more explicitly what we're dealing with here. So you have the first order, from Star Wars, numbers up to myriad of myriads. $10,000 times 10,000 equals 100 million. Which in his notation was just this here, caret symbol right over there. Though of course he didn't write caret symbol, but here we are. First order being numbers up to myriad of myriads. Second order, numbers up to a myriad of myriads squared. So you take this and here we go. So simple enough, and you just do this iteratively. But let's discuss exactly what happens as we get higher and higher and how the notion of Archimedes' periods comes about here. what is this sand reckoner? Exactly. It's the estimate of the number of grains of sand in the universe. This was actually the 8th order in the Archimedean system, which was equivalent to 10 to the 8th, to the 8th, 10 to the 64, at least in his system. And so that's a pretty big number. How far exactly that is from the real one, I can't exactly remember. But with Archimedes, things are often surprisingly close, and we'll get into that. So, what are these periods? Well, they organize themselves by 1 to 8th, 9 to 16th orders, 17th to 24th orders. Each of these makes up one period. So the 1st to 8th orders make up the first period. The 9th to 16th orders make up the second one. 17th to 24th, the third, and so on and so forth. Fairly interesting. And this is a pattern that echoes itself throughout Archimedes' works. Is this building upon building, not quite reaching the infinite, as we mentioned earlier, with the lack of a formal definition of a limit within the Hellenistic context of these times, but nevertheless yielding fantastic results. That I, for one, would simply have a hard time getting to if I were born in such an age as this. Now, let's get back to that pesky circle business. How can you get closer and closer to approximating pi accurately? Which pi is the circle's circumference over the diameter. That's the ratio. I didn't mention that earlier. So what's interesting is we ask ourselves, what is the ratio of a circle's circumference to its diameter? Archimedes comes up with a really clever solution. He comes up with an algorithm by which he uses regular polygons with doubling sides from a hexagon to a 96-agon to enclose the circle, each iteration approximating a circle more than the previous. He trapped pi to be between 223 over 71 and 22 over 7. And this is actually the best estimate in antiquity. With every new polygon, the approximation tightens. This method of convergence, long before the formal concept of a limit existed, Archimedes found a way to approach the infinite step by step using only geometry. Let's take a look at what that looks like more explicitly. So let's say you have your circle here, and this is a six-sided polygon on the inside. Let me draw it. Or try to draw it. There we are. Oh boy, okay. Alright. There we go. Not quite a perfect circle, not quite a perfect six-sided polygon. But you get the idea. Now let's break this down. There we go. Six-sided polygon, simple enough. What happens if you go to 24? There's better depictions of this online, but why not? 12-sided. Alright, I'm not even going to really attempt to draw that other than to show the basic partitions of this first. Got ourselves a little weird looking Union Jack there. And it's not even close to what I need to draw completely. 1, 2, 3, 4, okay. 1, 2, 3, 1, 2. Oh boy, okay. 3, 1, 2. Okay. Just assume that that's right as rain. And you can see what's going on here with the edges. It's getting closer and closer to filling up the total area of that circle. And it's a lot easier to get these individual segments than trying to do the whole thing full scale. And you can extend this into 24-sided polygon, 48-sided polygon, all the way up to the 96-sided polygon, and that's where his approximation gets us. Approximation is not a failure, it is a method for Archimedes. The infinite can be approached through reasoned steps. Now, another question. Can a curve square a circle or trisect an angle? The invented curve here, the spiral r is equal to a theta, becomes a tool for construction beyond straight edge and compass. The spiral enables the trisection of angles and squaring of circles. The kinematic insight here, Archimedes used double motion, radial and rotational, to find tangents, anticipating velocity vector analysis. Spiral-based trisection, A dynamic point traces the spiral while its base rotates uniformly. Movement creates shape. Shape enables thought. From kinematics, Archimedes distilled further geometry. Let's ask ourselves another question here. What's the area under a curved sky? What's the area under a parabolic arc? Here's an interesting way to prove, to find that. Say you have your, let's get rid of that. Say you have your parabolic arc. And then you can construct a converging geometric series of inscribed triangles. Let's call that B, this A, this C. Let's construct another triangle. Oop, oop, oop. PQ. Cursive triangle approximation of a parabolic segment. The total area forms a geometric series. Infinity can be reasoned about without being reached. This is a sort of proto-calculus in rigorous geometric dress. And we see that a lot, as we did earlier in the in the Hellenic foundations. Earlier Greek thought, creating these echoes that would spread later on to the minds of Newton and Leibniz. Let's move on to another question that further reveals this deep intuition. Can you measure a 3D curved space? The goal here is to find volumes, solids, like ellipsoids, and paraboloids. Let's take a look at an example in which Archimedes did actually measure a 3D curved space. And the parabola. Oh, okay. Here we go. oops, down a little bit. Let's say this is over here. Can I go ahead and redraw the parabola to match up a bit better? So the depiction is a lot nicer than my drawing. Okay. And there we are. Grid slices through a curved solid allow upper and lower bounds for volume estimation. Here, Archimedes effectively creates solid integration techniques before the concept of a limit. So you can kind of see the idea of a, well, sort of a Lebesgue integral in a way, but it's a Riemannian sum, I guess, in another. So the third dimension is no barrier. Geometric imagination can reach into the solid and carve truth. Now let's look into another such instance. As interesting as the man was alive, he wanted an equally interesting marker for his death. What shape did Archimedes want for his tomb? A sphere inscribed in a cylinder, the ratio of the volumes being 2:3. He wanted to figure out what would be the exact volumes of each of these shapes. So what he did, as I'm sure you can imagine, is first of all, inscribe another shape within another shape to get an easier approximation. Oops. Sphere inscribed in a cylinder. Volume and area results follow from comparing circular slices. And with that, he was able to say that the volume of the sphere is 4/3 pi or thirds cubed. Surface area volume of the sphere and the surface area. Is equal to 4 pi r squared. So, oh, sorry. I said earlier that you wanted to find the volume of the cylinder. That's not entirely accurate. You just wanted to find the volume and surface area of the sphere embedded inside of the cylinder such that the ratio of volumes is 2:3. So we have here a sphere described as a cylinder with volume and area results following from comparing these circular slices all the way up the cylinder here, at least in the area in which the sphere occupies. With this, mathematics leaves monuments. The sphere and cylinder is to not just describe, but to prove. What's a shoemaker's knife? The parabolas can be defined as a region bounded by 3 semicircles. Forming a crescent-like shape. Such as the shoemaker's knife, at least in essence. Back in these days, we had a lot more shoemakers, not just factories, and then take a knife that was shaped like so. Let me just go ahead and show the figure here. A circle drawn with diameter along the perpendicular from the cusp by 6. Oop, and oop. AC, here's E. It's kind of just like that, something like that. Evolutes and the surprising equality of the areas within a constructed circle. A circle drawn with diameter along the perpendicular from the cusp, Archimedes found, bisects the area of the parabolas. Even an oddly shaped region can have hidden structure. Geometry reveals equality where intuition itself does not yield fruitful results. It's kind of similar to some probability theory that would come later on in the days where intuition doesn't exactly match up with proven theory. Let's look at another question. can you trisect an angle by touch? Classical constraint. Trisection is impossible with straight edge and compass alone. Archimedes invents a tool called the noesis, placing a fixed length segment to meet two constraints simultaneously. Let's go ahead and draw this out. Archimedean trisection using a circle and insertion, the noesis, of a length segment. When rules are bent, understanding grows. Trisection with the noesis shows how constraints inspire creativity. Similar to how, I suppose in the 1950s, you see a lot of, well, it's sort of around the golden age of film. A lot of constraints leading to these very interesting products, these interesting works of art, like Casablanca, Rebecca, all of the movies with Gregory Peck. Let's look at another problem. How do you subtract angles before sine? Ooh. Nearly as bad as circle as usually do. And there we go. Chord split unevenly is bisected by a perpendicular from the arc's midpoint. The broken chord and its bisecting property leads to a geometric precursor to trigonometric identities. It's one of the things that Archimedes found with this is a pre-trigonometric structure that mirrors what sine subtraction will become. So he finds with this an analog to sine of x minus y equaling sine of x cosine of y minus cosine x sine y. the broken chord theorem. Geometry was already doing trigonometry. It just didn't have the words yet. He was able to solve all of this, find all of this. He didn't exactly have sine, but he was able to find it through geometric means alone. Let's go on to another such example of him doing that. Should do for today. What are the greatest proofs? Or warm-ups? There's this notion of balancing to discover area in an algorithm known as Archimedes' method. It was rediscovered in a palimpsest in 1906. The core idea behind it is to treat area as made of infinitesimal slices that balance like weights on a lever. You can see echoes of the fulcrum idea emerging here. So, let's do fulcrum. Let's get these slices. The parabolic segments area found by balancing slices about a fulcrum. Exactly what we were talking about here earlier with the core idea. Now we can take this even further. Suppose this is the case. Supposed to, dang it, okay. So pretend the triangle just sort of touches that upper bit of the circle there. sort of morphing my circle into not a circle. But the idea here is that cross-sectional balancing of circular slices from cone, sphere, and cylinder along this same core idea that you can balance this like weights on a lever. And this extends to a pretty neat example of it being done on a cylinder with parabolic. Oh. Well, yeah, use a little. Oh, let's go ahead and drop that. Then you can just like so. You can use, well, the intersecting cylinder volumes used to model solids and discover volume relationships was also discovered by Archimedes. Archimedes wasn't just solving problems, he was inventing methods 2,000 years before calculus. So some of the core things we looked at here were balance, infinitesimal reasoning, mechanical analogy, constructed geometry, leading to a mathematical identity in which the physical geometric unification of math and nature is met. Truth, as it's understood, is what balances, what converges, what builds. Archimedes turned geometry into a science of matter and a philosophy of proof. He lived in a city at war, but his mind moved in perfect balance. Now, think to yourself, suppose you're Archimedes, the world is at war, the Romans are invading, but you are bent over a parabola, proving that its area is 4/3 that of its triangle. What does that say about what you believe math is for? Well, let's describe another one of these mathematical titans, Apollonius of Perga. This is around 262 to 190 BC. Perga is, you all know where Turkey is, at least I hope so. This is not the best drawing, so I certainly hope so. Like a little bridge to Constantinople with Constantinople on it. You have Greece over here and all that stuff. Perga was a city, it's close to Cyprus if I'm not mistaken. Close to Cyprus, I think. Working from memory on that one. Yeah, somewhere up in there. Not entirely sure. But with that, I welcome you to mathematical high renaissance of antiquity. Apollonius, seen by many as the heir to Euclid and Archimedes, took the simple idea of slicing a cone and birthed the geometry that would guide Newton to the stars. This wouldn't be mathematics for artisans. This is mathematics as metaphysics, a continuation of that Greek tradition, in which we blend the religious nature of what Greeks viewed mathematics with later tools, and theory upon theory, no longer a bunch of detached things whose purpose solely revolves around the pragmatic goings-ons of bureaucratic taxation and land grants and contracts we saw much earlier. So let's look at problem. Can a single cone give rise to all curves? Before Apollonius, mathematicians believed each conic type, ellipse, parabola, hyperbola, required a different type of cone, a different kind of cone. Apollonius showed that by slicing a single double-napped cone at different angles, one could generate all three types. Shouldn't be touching there. There we go. Something like that. Basically here. C. The diagram shows a planet tracing an epicycle, small circle, whose center moves along a different large circle. The drawing later reflects Apollonius' core insight. Nested rotating motion can be reduced to pure geometry. A single shape, the cone, hides a multitude of curves. This teaches students the power of unity within variation. And we'll get more into this. Because it's kind of abstract. Okay. Yes, okay. What's the curve whose name means deficiency? So what's interesting is these curves were all given names. The ellipse, squared, let's go ahead and make it fancy L, which means a deficiency. Parabola. Just right. Hyperbola. And you see this idea of balance again with the Greeks. Nothing in excess, know thy limit. These are the words most etched on the walls at the Oracle of Delphi. Or Delphi. One of them's right. I just don't know which. So the names are not just vocabulary here. They express the relationship between squared distances and linear terms. Ontology here means what kind of thing something really is. Apollonius wasn't just naming shapes, he was classifying mathematical realities, similar to the way in which Archimedes was looking at these different orders and classifying them under different periods and so on. Just check the camera. Now let's look at how this relates to the cone from earlier. Circle, ellipse, parabola. Oh, oops. Parabola. There we go. And hyperbola. Cone is as such. Parabola. Finally, the hyperbola. All represented in cones, and not different cones, the same cones. Like two-dimensionally, of course. The usual up. And this one here. As such, all before coordinates. Now, how do you define a curve without an equation? Modern times, this seems quite silly, but we're used to geometric intuition by now. Apollonius used a cone and slicing planes to define curves long before coordinates were invented. The goal for him was to turn a 3D cutting process into a 2D rule using only geometry. cone sliced by a plane, the result is a conic section, ellipse, parabola, or hyperbola, depending on the plane's angle. As I showed earlier, and let's get another example, hopefully better drawn. Here, ellipse. Okay. It's kind of hard to draw because I don't draw it big enough. So there we go. Okay, something like that. This is a geometric construction from the first book, from Proposition 3 of his Conics. It shows how to derive properties directly from cone geometry. Realization here is that Apollonius didn't need coordinates, he extracted laws from the shapes themselves. Now, here's another question. Can a line touch a curve without calculus? How do you define that? To any degree of approximation that's valuable. Because today we use derivatives to find tangents, but how did Apollonius do it without algebra or without limits? He used conjugate diameters, pairs of lines that define symmetry in ellipses and hyperbolas. The key idea being that a line tangent to a conic is the only one that doesn't cross it and just kisses it at one point. Any tangent to a conic touches it at a single point and intersects the asymptote symmetrically. Seeing this parabola here, and let's draw this. Construction of a tangent using harmonic division. Apollonius shows how to find tangents using only compass and straight edge. See, even without calculus, the Greeks had precise ways to find tangents using ratios, reflections, and geometry alone. Let's ask ourselves another question. What is the locus of a triangle's hidden center? Suppose you're given three objects, each either a point, line, or circle. Can you construct a circle tangent to all three? There are 10 distinct cases, depending on the combinations of objects. The most famous is the 3D circle, or the CCC case, which can yield up to 8 distinct solution circles. This is an early example of a deep locus problem. Identifying all points, here centers of circles, satisfying geometric conditions. A historical note here is that this problem does not appear in the surviving books of Apollonius' Conics. It is known through a summary in Pappus's mathematical collection, where it is attributed to Apollonius' now lost work, Tangencies. Pappus reports that Apollonius solved all 10 combinations of point, line, and circle. There are several modern connections. Vieta rediscovered and expanded the problem in the 1600s. Descartes gave an algebraic solution, which came to be known as Descartes' circle theorem. Soddy, in 1936, gave an elegant poetic solution in Nature. Epstein, in 2001, and others have reconstructed solutions using both classical and computational methods. Let's look at one real quick. Okay. Probably not going to have a lot of room here, so I'm going to right at the top part. Or maybe not, maybe not, maybe. So. One, two, three, 4, 5, 6, 7, 8, 'The most general case of the problem of Apollonius, finding circles tangent to 3 given circles. Depending on the arrangement, up to 8 distinct solution circles shown here may exist. And this is taken from Gish and Rabondo 2004. So even without coordinate geometry, ancient mathematicians could pose, and in some form solve, problems that still challenge and inspire mathematicians and computer scientists today. So let's move right along. What is the shape of a planet's path? You didn't quite get it right this time, but that's all right. So earlier, astronomers like Eudoxus used nested spheres. Apollonius introduced this notion of the epicycle, circles on circles. This was to model planetary motion more precisely. You can describe complex looping paths using only circular motion. The figure that I showed earlier applies here. Let's get them more. There we go. Up. Up. Go. A visual model of epicyclic motion. The planet moves around a small circle whose center moves around a larger circle. What looks chaotic, like planetary retrograde motion, can emerge from simple, elegant geometry. Let's ask ourselves another question, and then we'll go ahead and wrap this up. Can you construct, not yet, well, can you construct the normal to a curve without algebra? A normal is a line to the tangent at a point on a curve. Apollonius found normals by finding shortest or longest distances from a point to the curve before analytic methods existed. He also effectively discovered the evolute, the curve tracing the centers of curvature of another curve. Oh, let's go ahead and that's what I get for trying to rush this drawing. This is nonsense. Okay. Apollonius uses minimum length reasoning to define the normal to a parabola, an early precursor to the derivative. Geometric construction of a normal form, of a normal from an external point using an auxiliary hyperbola. See, without symbols or calculus, Apollonius still traced the core ideas of curvature and optimization, things that would lead to even greater fruits in subjects like numerical analysis. So the core principles we looked at were geometry as ontology, locus as solution, reasoning without coordinates. This led to a mathematical identity of civilization, of ideal forms and logical precision. A mix of Plato and numerical analysis, I guess you could say. Algorithmic approximation. This leads to a concept of truth that it is that which is shown in space and follows necessarily from form. Apollonius did not merely study curves, he turned geometry into a cosmos. Suppose this: you are Apollonius, no symbols, no variables, only cone, plane, and reason. Construct a line that touches a curve and prove that no other can do so. And with that, I end today's lecture. And that should be it.